So we are moving forward to quarterfinal number 2 of the 2025 MIT Integration Bee, where the first question was the limit as a tends to infinity of the integral from x tending to negative infinity to x tending to positive infinity of a over a squared times x cubed minus 3x close bracket squared plus 1. Problem number 2 happened to be the indefinite integral of 1 over product of cosine x plus 2 pi over 3 cosine x minus 2 pi over 3 all squared. Problem number 3 was the definite integral from x equals to 1 to x in 2025 of the ceiling function of 2025 over the floor function of x, or the floor of x, minus the floor of 2025 over the ceiling of x. Very interesting problem. We'll see how we may be able to solve it. And then there was a tiebreaker problem. This was tiebreaker number 4, since in the first quarterfinal they ended up going through 3 tiebreaker problems. So the fourth tiebreaker problem was x plus 1 times e to the power x times the natural logarithm of x. So these are the problems that we'll be looking at today. We'll go through them methodically, step by step, just elucidating some of the steps that needed to be undertaken to get to the answers. So if you have any questions, we do ask you to leave a comment or two, or you can reach us via email. But this is our joy. We do love going through mathematics, solving numbers, and we hope you share in our passion. So let's move forward and begin on this journey. So with this problem, as a tends to infinity, it means that a is such a large value. What happens here is, let's first of all begin by factorizing the component next to a squared in the denominator. So when I pull x out, it becomes x squared, since we have a square here. And then we have x minus, since we were left with x squared minus 3, so difference of 2 squares, we have x minus 3, root 3 squared times x plus root 3 squared plus 1. So this is just a factorization of this expression here. And it's going to be crucial because, as we see here, this integrand really, it tends to 0 at all points except when x is 0, or when x equals to root 3, or x is equals to negative 3. So what this tells us is that we have a Dirac delta-like function at these points. And so our integration is going to be focused at x equals to 0, x is equals to positive root 3, and x equals to negative root 3. So now, using Taylor's expansion or Taylor's approximation, we're going to look what this function looks like at the points 0, x equals to positive root 3, x equals negative root 3. So Taylor's expansion is just that when we have fx, it equals to f of x naught, that is at these points, 0, point root 3, negative root 3, plus the derivative of this function fx with the specific points x naught substituted in times x minus x naught, and so on and so on and so on. So we're just going to look at the first part of this approximation. Since fx naught is going to be equal to 0 at those points, the first approximation here is going to be equals to 3x naught squared minus 3 times x minus x naught. So we're going to say that, okay, at x equals to root 3 negative, the value is obviously using this, it's 3 times negative root 3 squared, which is 3 times 3, which is 9, minus 3, which is going to be 6. And then x naught is negative 3, so we have x plus root 3. At x equals to positive 3, on the other side, we have 6 times x minus root 3. And finally, in between x equals to 0, we have negative 3x. So this lower part here approximates to these values. And so what you could do is you could look at it as if we have 3 different delta Dirac functions that we can integrate separately with the Dirac delta function at x equals negative 3, taking this integrand with x cubed minus 3x being equal to, or being approximately equal to 6 times x plus root 3. And equally at x equals to 0 and at x equals to positive root 3, we do the same thing. And that's what we're going to do. We said we could break down our integral, assuming that we have now 3 different delta Dirac functions, delta Dirac-like functions. We can now say, okay, let's integrate the first function for which this expression is around x equals negative 3, root 3, and then when x is around 0, and then when x is around root 3. Okay, and so we can now go ahead and try to substitute this off. So let u, I'm just using a general expression here, let u be equal to a times 3x naught squared minus 3 times x minus root 3. So du dx, differentiating both sides with respect to x, we get on the right hand side a times 3x naught squared minus 3. And we can divide both sides by 3x naught squared minus 3, so we have 1 over 3x naught squared minus 3 du, and equals to a dx. Okay, so breaking down this or substituting for u for x in place of with u, we get for this specific area, we have u in place of this, but obviously a dx becomes 1 over 6 du. And then the same thing happens for this. This becomes u squared, and a dx becomes negative, so we have 1 over 3 here, plus, and then this is 1 over 6. And so we can now factor out the constants. These negatives cancel, so we have 1 over 6 times the integral from x equals to x tending to negative infinity to 8, to x tending to positive infinity, of 1 over u squared plus 1. Just factoring this out, we get the same integral for all these constants, and we add a 6 and a third and a 6. This becomes 2/3 this integral that is famous. So we know this integral to be amounting to the arctangent of u with the limits negative infinity, positive infinity. As u tends to positive infinity, the arctangent of u is pi over 2. As u tends negative infinity, the arctangent of u is negative pi over 2. Adding those together, we get pi. So the answer here is really 2 pi over 3, and that's what was expected. So the next problem here, problem number 2, 1 over cosine x times cosine x plus 2 pi over 3 times cosine x minus 2 pi over 3. So the first thing I'll do is use cosine a plus b being cosine a cosine b minus sine a sine b. Cosine a minus b is cosine a cosine b plus sine a sine b. So when you add both sides, you get the fact that cosine a cosine b is half cosine a plus b plus cosine a minus b. So focusing on these two parts here, we can now have our integrand being 1 over a plus 2 pi over 3 plus x minus 2 pi over 3 becomes 2x, and then when you get the difference, it becomes 2 pi over 3 minus 2 pi over negative 2 pi over 3 becomes 4 pi over 3. And so we have cosine x times cosine 2x plus cosine 4 pi over 3 over 2, and we still have a square here. So what happens is we can pull that 2 out so that it becomes 4 in the numerator, and then we can now multiply cosine x across to cosine 2x and cosine 4 pi over 3. And cosine 4 pi over 3 is same as cosine pi plus cosine pi over 3. So this is in the third quadrant. So this value is just going to be equal to negative cosine pi over 3, which is negative a half. So multiplying cosine x and cosine 2x becomes something that we can also use the previous expression where we're saying that cosine a cosine times cosine b is equals to a half cosine a plus b plus cosine a minus b. And so a plus b is 2x plus x, which is 3x. A minus b is 2x minus x, which is x, and so which becomes cosine. So let's put that into writing. So we have 4 1 over cosine 3x plus cosine x over 2 minus a half cosine x, right? And so this becomes this and this cancel each other. So you have cosine 3x over 2, pull the 2 out, square 16, and we have cosine 3x. You square that, we get 16 times 1 over cosine squared 3x. And that means that we have the integral of 16 times 16 times the integral of sec squared 3x, and that is a popular integral. The integral of sec x squared is tangent of x, but we have 3x instead, so we have 16 over 3 tangent of 3x plus c. So the answer expected, the integral from of 1 over cosine x times cosine x plus 2 pi over 3 times cosine x minus 2 pi over 3 all squared, is equal to 16 over 3 tangent 3x plus an integration constant. And that was the answer that was expected. On to problem number 3, the definite integral from x equals to 1 to x equals to 2025 of the ceiling of 2025 over the floor of x minus the floor of 2025 over the ceiling of x. So let's begin by defining what a floor and a ceiling is. So for the floor of x, that is equals to k when x is greater or equal to k and less than k plus 1. So in other words, when x is between k and k plus 1, but not k plus 1, that the floor of x is k. And then the ceiling of x is equals to k plus 1 when x is less or equal to k plus 1 and greater than k. Okay, so for our situation here, we see that this first expression will be equal to 2025 over k. and we have to sum, because now we have to discretize this integral into 2024 different expressions. So we have 2025 over k minus 2025 over k plus 1. Okay, and this is important because we're beginning from 1, and from 1 to 2 this ceiling becomes 2, right? And in that interval the floor is just 1. Okay, the reason we did not go up to 2025 is because that is the limit. We don't have the interval 2025 to 2026, so our k stops at 2024. The 2025 is just an instantaneous value, and so the dx here tends to 0 at 2025. Okay, now we go ahead and see that now we have to express this just to understand what is happening. 2025 ceiling over 1 minus floor 2005 over 2 plus the ceiling 2025 over 2 minus the floor 2025 over 3, and so on up to the very last where we have 2025 over 2024 ceiling minus floor 2025 over 2025. It's important to see that we have expressions with similar denominators here. We can try to batch those together so that now we have 2025 over 1 ceiling plus brackets the ceiling of 2025 over 2 minus 2025 over 2, that's floor, and so on until the last where we have the ceiling of 2025 to 2024 minus 2025 over 2024 minus the last floor 2025 over 2025 floor. So it's very crucial to see that the floor and the ceiling will be different from each other by a value of 1, and they'll only be equal when the values under those functions are integer values, right? So for example, that happens when the integer in the denominator is a factor of 2025. For example, if we have 2025 over 25 or over 5, that will become so 2025 over 5, we get 405. So the floor of 405 and the ceiling of 405 are equal, so that value becomes 0. So we have to find how many factors lie between or how many k's between 2 and 2024 factors of 2025, right? And how we do that is we say, okay, we have 2025, divide by 3, you get 625, divide by 3, you get 225, divide by 3, you get 75, 75 divided by 3, you get 25, 25 by 5, you get 5, right? And so what that means is that having done this, all the factors of 2025, and we denote that set by f, 2025 is either 3, 3 times 3, 3 times 3, 3 times 3 times 3, 3 times 3 times 3 4 times, and then 5, 5 times 5, 3 times 5, 3 times 5 times 5, 3 times 3 times 5, 3 times 3 times 5 times 5, 3 times 3 times 3 times 5, 3 times 3 times 3 times 5, 3 times 5, and then 3 times 3 times 3 times 3 times 5 times 5. We missed one here. So and then so that becomes 3, 9, 27, 81, 5, 25, 15, 75, all the way up to 2025. And so factors from 2 to 2024 this, we're going to exclude the 2025. So the number of these factors, or the cardinality of this set that we're proposing here, is essentially 13. So we're going to exclude 13 ones between in this expression we have here, because in those instances whatever is in the bracket is 0. Out of those instances, whatever's in the bracket is 1. So we're going to have now 2025 plus 23 different brackets here, sets of brackets, minus 13, and then minus this one here. So we have 2025 plus 2010 minus 1. And the answer that we expected there was 2034. So that is the answer that was expected. Pretty interesting, but required a lot of thinking and putting it into an answer. The tiebreaker problem. This is an easy one. So first thing is, I would want to express e to the power x as the derivative of, let's first of all just expand it out. So we have x times e to the power x times natural logarithm of x plus ex natural logarithm of x. And so focusing on this first integral here, after dividing this into two separate integrals, means that we can express this e to the x as the derivative of e to the x. And the reason I'm trying to do that is because I'm trying to exploit integration by parts. So x times natural log of x times the derivative of e to the x plus the integral of e to the x times natural logarithm of x. And so since integration by parts means if you have a product of v and the derivative of u integrated, means that is equals to uv minus the product of u times the derivative of v. And so in this scenario here, this is our u and this is our v. So uv is x times e to the x times log of x, right, minus e to the x, which is our u, times the derivative of x times log x. This is our v. And so what that means is x times e to the x log x minus e to the x. This is a product of two functions, that is x times the derivative of log x plus log of x times the derivative of x. And so expanding it out, derivative of natural logarithm of x is 1 over x, this divide, and so the derivative of x is just x, so we have log x here. And so we can now expand this out and see that we have x times e to the x natural logarithm of x minus e to the x, right? Again, minus e to the x times natural logarithm of x plus the natural logarithm of x. And these two integrals cancel each other, so we are left with this one integral to now solve out. And so the integral of e to the x is just e to the x. And so our answer is simply x times e to the x times natural logarithm of x minus e to the x plus the integration constant. And so our final answer is the integral of x plus 1 times e to the x times natural logarithm of x is x times e to the x times natural logarithm of x minus e to the x plus integration constant. Or you could factor out the e to the x so that we have e to the x times the x times open bracket x times the natural logarithm of x minus 1 close bracket plus the integration constant. And that was the answer that was being sought.